Today we're going to talk about the solutions. Now let me turn that on. So we're going to talk about definitions of the solutions. Trying to find out. Okay, awesome. So what are the solutions, the true solutions? Solutions are homogeneous mixtures. You remember we were talking about homogeneous mixtures, the ones that cannot be separated by filtration or any other physical, like mixtures that cannot be separated by simple physical methods like filtration or sedimentation. So solutions can be formed when the molecules of solvent form significant attractive forces with the molecules of solute. And we'll get back to that attractive forces in a moment, but first we need to identify what is solvent and what is solute. So solute is the chemical that is present in a smaller amount than the solvent. So in the solution of, say, salt and water, salt will be always in the smaller amount than the water because solubility is limited. So water here will be a solvent, yes, and the salt will be solute. So far, make sense? Now, we used to think about solutions as something liquid, like the solution of salt. It doesn't necessarily have to be this way. Turns out, solutes by themselves may be liquids. For instance, you can have a solution of one liquid, say alcohol, ethanol, in water, okay? Solutes can be gases. Any water sample will contain oxygen and nitrogen and carbon dioxide. Carbonated water is basically a solution of carbon dioxide in water. Solids can be, well, solids. That's an example of the solution of salt. Okay? That makes sense? So initially salt is solid, but when you add it to water, it dissolves there. So far, we good? Mm-hmm. Important thing is that when dissolved, solutes spread evenly at the molecular or ionic level. So when you dissolve salt, I'm kind of giving you sort of a heads up to what we're going to talk about. But salt dissociates into sodium and chloride ions, okay, and evenly distributes throughout the solvent. When you dissolve glucose in water, glucose molecules evenly dissolve in the water, okay? What's important is that solvent and solute have the same physical state. If you would look at salt, like sodium chloride or baking soda, they're solid, water is liquid. You mix them, you let your solute to completely dissolve in water, and now you have entirely liquid solutions. No hard particles, no solid particles. Does that make sense? For instance, if you will take sand and mix it in, it's not going to dissolve, it's still going to contain the solid particles. Therefore, solutions cannot be separated by simple filtration. You can separate them by evaporation, no? You get a salt solution, heat it up, get the salt. Think about seawater. Seawater is the solution of a huge number of different salts. And if you will evaporate seawater, you will get what you can buy in the grocery stores, the sea salt, right? Water goes away, the solvent goes away, and what you have left are all your solutes. And solutes in the true solution are never visible. They can give it a color, but never visible. As we experienced in the lab, if you take blue copper sulfate and add few crystals to colorless water, the solution turns blue. You know, it's still liquid, but it's just blue. Does that make sense? So here, that same example, in the left cylinder, you can see copper sulfate being at the bottom of the cylinder and water above it. And then after a while, copper and sulfate ions, they dissociate and they become dissolved and they become a part of the solution. What's important to understand, so think about this, if you will leave copper sulfate solution for an extended period of time in the can, nothing's going to happen to it. It's not going to separate. Does that make sense? You need to evaporate it. Yes, then it's going to work. But other than that, it's not going to separate. We clear so far? So this table gives you some interesting examples of solutes and solvents in different solutions. So first, I want to chat with you about the liquid solutions. So for instance, carbonated water that I already used as an example is the solution of carbon dioxide in water. The household ammonia, so basically the same solution that you use to clean the glass, okay? That one is the solution of ammonia gas in water. In fact, the ability of ammonia gas to dissolve in water is absolutely outstanding. If you take 1 liter of water, you can dissolve up to 700 liters of ammonia gas at the room temperature and the normal pressure, atmospheric pressure. It's incredibly soluble. Does that make sense? Mass-wise, it's a different story, but volume-wise, it's unbelievable. Liquid and liquid, well, vinegar or vodka, which is more fun, okay? Still, it's the solution of liquid. In case of vinegar, it's going to be acetic acid. In case of vodka, it's going to be ethanol in water. So far, we good? Solid and liquid. We already used seawater. Now, in order to get away from water as a solvent, another example is the solution of iodine in alcohol. It's called a tincture of iodine, and it is often used for the antiseptic treatment of the skin. Here, I don't know, can you buy betadine in the pharmacy over the counter? I'm just not aware. You can? Yeah. When I was a kid growing back in Russia, like iodine tincture, the first treatment with any bruise or, cut or anything like that, just to clear the skin. There are solutions of gas in a gas, and we breathe one, the air. It's the solution of oxygen and carbon dioxide in nitrogen. And there are solid solutions. For instance, brass, the solution of zinc in a copper, okay? Or steel, the solution of carbon in iron. They're both true solid solutions. You cannot separate them by filtration, for instance. You cannot, so in both steel and brass, you cannot see sort of chunks of solute suspended in the solvent. Atoms are evenly distributed throughout. Does that make sense? I don't recommend it, and you probably don't have means to do that, but you can actually make metal and metal solution yourself, solid and solid. It's kind of a weird solution. When I was in college and we worked with mercury, when you have a spill of mercury, there are 2 ways to collect it. If that's a large amount, you have to have a vacuum. I mean, not a household vacuum, just a hose with a vacuum and you suck it in, okay? Simpler way to collect very small amounts of mercury, you take a penny, anything that contains copper, and you touch the mercury. And mercury immediately forms a solution of the copper on the surface of the penny. It looks absolutely glorious. It's the shiniest piece of metal that you will ever see. Now, from the biological standpoint, I try to use pennies to collect pretty substantial amount of mercury once. It's exhausting. You have to have like a bag of pennies to do that. And then what you're going to do with those? They still contain mercury. You still have to put them somewhere. Anyway, water is the solvent. Why we so focused? Why we always talk about water? Why we never mention, I don't know, acetone or ethanol or, I don't know, anything else? Sulfuric acid, for instance. Water is the basis of life. Human beings consist of water by 60 to 70%. So no wonder that properties of water solutions are of particular interest for us, since, we try to make a connection between the chemistry and biology of a human. So water molecules are polar, okay, because bond between oxygen and hydrogen is a polar bond. And that explains that water forms hydrogen bonds with many other compounds. And that explains how water can dissolve huge biological macromolecules like proteins or nucleic acids or carbohydrates, but on the other hand, repels hydrophobic molecules like lipids. So, when you think about the formation of a solution, you're basically talking about a very schematic process which involves solvent, right, and the solute. Does that make sense? Particles in a solute, whether those are ions or molecules, they interact with each other. Does that make sense to you? Say in the sodium chloride, positively charged sodium and negatively charged chloride interact with each other. So in order to make a solution, you have to first break that bond, right? And then sodium and chloride, each individual ion, they have to establish some kind of interaction with the molecules of solvent, say water. Are you following me? So basically, it's like, these two are friends, and in order to get them in your community, you have to break their friendship, but give them in return something stronger, something more attractive. So basically, the interactions between the solute and solvent have to be strong enough to overcome the price of breaking down solute-solute interactions. Does that make sense? You understand what I'm trying to say? So when you dissolve something, it has to be beneficial. It has to provide some kind of a benefit from the energy standpoint. Okay? That makes sense? For instance, here in this illustration, you can see different non-polar fluids not mixing with water. Why that's so? Well, because water, in our case, solvent, is polar, right? And something that we try to dissolve, let's say benzene, or gasoline, or cyclohexane, is nonpolar. So water molecules cannot interact efficiently with the molecules of, say, cyclohexane. Does that make sense? Since they cannot interact, they cannot provide that energy benefit, the solution will not form. You can see that situation when you mix oil and water. Okay? Oil is nonpolar, water is polar. That's the simple explanation why these two compounds cannot normally interact, cannot form a true solution. Does that make sense? The general idea is that like dissolves like, meaning that polar compounds will more efficiently dissolve in polar compounds and vice versa. So basically, you can expect fat, like animal fat, solid fat, to dissolve in plant oil, but not in water, because both fat and oil are non-polar. Does that make sense? And you can expect, it's particularly important for gases. Remember what I mentioned about ammonia gas? That it has crazy solubility in water. Ammonia gas is a polar molecule, very polar molecule. It's a dipole. Water molecule is also polar. This is why ammonia dissolves so well in water. If you will take oxygen, which is totally non-polar, it is very poorly soluble in water. Does that make sense? And if you want a link to human physiology, I can give you one right away. Anyone knows which cells in the human body carry oxygen? Red blood cells. And how they carry it? Oxygen is bound to the atoms of iron, which are in turn the part of the molecule of hemoglobin. Oxygen cannot be carried simply by the plasma, because plasma is mainly water. It doesn't dissolve oxygen. Does that make sense? On the other hand, carbon monoxide is crazy soluble. Okay? It also interacts with hemoglobin, but it's also crazy soluble in plasma, because it's a polar molecule. That makes sense? So it's important to remember that polar solvent will likely form the solution with a polar solute, and nonpolar will form a solution with nonpolar. Are we clear about that? Now, I started the chat about sodium chloride. I never managed to finish it, and now I have a chance to do that. So if you have solid sodium chloride, basically the table salt, and you mix it with water, during the process of dissolving the salt, salt will dissociate into sodium cations and chloride anions. You have to understand that. These cations and anions, they do not exist as naked ions, naked charged particles. They are surrounded by the water molecules in the solution. Chemists often use the phrase or the term hydrated ion. Okay? Hydrated means that the ion is surrounded by the molecules of water. Does that make sense? And basically what you see here is that, do we spend some energy from breaking that ionic bond between sodium and chloride? Do we have to invest some energy to break a pretty stable bond? Absolutely, yeah, we have to. But it turns out that when sodium ion and chloride ion start to interact with the polar molecules of water, the hydrogen bonds that they establish here provide energy benefit. So there is more energy released in this process than the energy we use to break sodium chloride into ions. Does that make sense? So it's a beneficial trade-off. Okay? Same example, well, not the same example, but same idea governs the dissolution of alcohols in water. If you will take rather small alcohol molecules like methanol or ethanol, which is not in the picture but same idea, okay? So in methanol there is one carbon. Okay, can you see that? So that bond between the carbon and the oxygen is very polar. So methanol is very well soluble in water. If you take ethanol, which has this structure, now you see it has two carbons. So what do you think about this bond? Is it polar or non-polar? Between two carbons. Bond between two carbons. Polar or non-polar? Two carbons. Two identical atoms. It's non-polar, right? Nobody pulls electron density stronger than another. Does that make sense? Now this bond is polar, so we still have one polar bond, one substantially polar bond. Ethanol will dissolve in water fine. If you will take isopropanol, that's rubbing alcohol, it's going to dissolve in water just fine. But if you will go up and you will look at the molecule of, which contains, let's say, I don't know, 5 or 6 carbons, molecule like this, okay, at the bottom, can you see that? That's hexanol. Hexanol will be very poorly soluble in water. Because look how many polar bonds it has. 1, 2, 3, non-polar bonds, sorry. 1, 2, 3, 4, 5, right? 5 non-polar bonds. And then only one polar. So the whole molecule will have very little polarity. Does that make sense? So that again highlights that polar solutes will dissolve in polar solvents and vice versa. We're good so far? Now, electrolytes versus non-electrolytes. You've all heard, the phrase when you dehydrate, when you run in the heat, which as far as I understand will be extremely important in the upcoming Thursday and Friday. They promise some insane temperatures in Cleveland. You're going to lose not only water when you sweat, you're also going to lose some electrolytes. So what are those? In a human body, electrolytes will be sodium, potassium, chloride, calcium, bicarbonate, and we're going to lose it with the sweat. And the role of these ions is basically the same as we observed when we tested the conductivity of different solutions in the lab. Remember that story when you had this little electric device that you stuck in different solutions and the lamp either went off or didn't? Remember that? So these ions are essential for the proper transmission of the nervous signal. The nervous signal is essentially electricity, right? So basically those ions are essential for the electrical transmission in the human body. Okay? So without, what happens to you if you don't compensate for electrolytes? With your muscles. They start to cramp. And that's basically the failure of the muscles to properly transmit an electrical signal between the cells to initiate the proper controlled contraction. Does that make sense? This is why electrolyte balance is so important. So, electrolytes can be strong, can be weak, and there are chemicals that are not electrolytes at all. Strong electrolytes completely dissociate in water. And in this situation, the word dissociate doesn't mean that they split into individual molecules. The word means that they split into individual positive and negative ions. For instance, a solution of sodium chloride contains sodium cations and chloride anions. The solution of potassium bicarbonate will contain bicarbonate cations and potassium cations and bicarbonate anions. Does that make sense? So they dissociate. If you will put any source of electricity, and if you remember those little devices that we used, along with the lamp and some, for me, absolutely obscure electrical details, they had one very obvious electrical detail. They had battery, right? Each of them had battery as the source of electricity. So this is why the lamp went off, because electricity that was generated by that battery actually managed to get through the solution because of these ions. These ions move to the opposite poles. Cations would move to negative pole, anions will move to the positive pole. I know that there's a lot here pictured, so I'm going to get rid of something of it. And I just want to mention a couple of terms here. You've heard the term cathode and anode. So cathode is the metal rod that attracts positive ions. Anode is the metal rod that attracts negative ions. Does that make sense? Now, weak electrolytes do not completely dissociate in water. They form both ions and molecules. So this equation of dissociation of hydrofluoric acid shows you that the reaction, the dissociation reaction, is reversible. So there are some cations and anions, and there are some molecules. And this image here shows you the same. There are some cations, some anions. These charged particles will enable you to have the electrical current through the solution. But by sheer numbers, they won't be comparable to what we see in case of a strong electrolyte. Strong electrolyte produces much more ions to conduct electricity. Does that make sense? Weak electrolyte produces much less ions to conduct electricity. Understood? So that basically kind of tells you, in which body of water you have higher chances of getting zapped by electricity in case of, I don't know, some kind of electrical accident. Probably not in the lake. It's fresh water. But in the sea, absolutely. A lot of cations, a lot of anions, all strong electrolytes are there. Potassium iodide, potassium bicarbonate, sulfates, chlorides, sodium. All of that will facilitate the electrical transmission in the water. That make sense? Any questions so far? Now, non-electrolytes. Sucrose, glucose, anything that dissociates into molecules. Okay? So here in this case, individual molecules in the solution, they form true solution. Don't get me wrong, it's a true solution. But individual molecules, since they're not charged, they cannot carry electricity. So the solution of non-electrolyte will not transmit electricity. Does that make sense? And that kind of explains all those wonderful stories about people being on the, source of electricity. I don't know if you've heard that, but there was a story about one drunk. When I was a kid, we were always kind of scared that the guy actually found an electrical transformator, a gigantic device that converts the electricity that goes through the power lines into the household current, And this drunk, he peed inside. Urine contains a lot of electrolytes. So they found shoes. That's about it. He got zapped. All right. Okay. Now, examples of strong electrolytes are basically all water-soluble ionic compounds. Sodium chloride, sodium bicarbonate or baking soda, calcium chloride, sodium sulfate. I can just go on and on and on. Okay, strong acids are electrolytes. Weak electrolytes are usually weak acids, weak bases like water solution of ammonia. And non-electrolytes are most frequently water solutions of different polar organic compounds. Say, methanol in water doesn't dissociate into individual ions. It exists in the form of a molecule. Does that make sense? Got it? Now, when you read the blood work of a patient, often the concentrations of ions are expressed not in the concentration units, which we're going to be talking about, but in equivalents, or more frequently, milli-equivalents. So equivalent is, now bear with me, the amount of an electrolyte, or the amount of ion, that provides 1 mole of electrical charge. Let's pause for a second. And I want to ask you now, what is a mole? Say again? A number. And that is it. It's a number. Does that make sense? So 1 equivalent means that you have 1 mole of a positive charge or 1 mole of a negative charge. Are you with me? Now, do you remember what is the charge for the sodium cation? If it's cation plus how many for sodium? Just 1. So, how many moles of sodium cation should you have to have 1 mole of positive charges? 1. Right? Got it? Now, calcium. Anyone remembers the charge? It's also positive, but 2. So how many moles of calcium ions you gotta have to have 1 equivalent of charges? Too fast. Half the mole. Because each calcium gives you 2 charges, right? So you need only half mole of calcium ions, since each ion contributes 2 charges. Does that make sense? So calcium, contributes 2 charges. So each calcium ion will give you 2 charges. Half the mole will give you 1 equivalent. Same idea. Aluminum, which is 3+, you need 1/3 of a mole to get 1 equivalent of aluminum. Does that make sense? Because each aluminum cation gives you 3 charges. So if you have 1/3 mole of aluminum, the number of equivalents will be exactly 1. Got it? Same idea for anions, really. So say, if you talk about, if you talk about chloride anion, one charge, 1 mole of chloride anions, 1 equivalent. Does that make sense? Sulfate, half mole of sulfate anions, 1 equivalent. We're clear? Good. Now, since concentration is usually much lower, the ionic concentration in the blood and physiological fluids usually expressed in milliequivalents, 1,000ths. So these are the examples. Now, it is important because it allows you to address the question of how many solutes in general you have. For example, imagine that you have a solution, a mixture of a solution of sodium chloride and potassium chloride. And you know that there are 25 milliequivalents per liter of sodium and 4 milliequivalents per liter of potassium. So the total positive charge of the solution will be 29 milliequivalents per liter. Does that make sense? Meaning that 1 liter of your solution contains 29 milliequivalents. Positive. And it must contain the same amount of negative milliequivalents. You always have positive and negative charges balanced. Are we clear? We good? So, sometimes you have to convert equivalents into the concentrations. So how you do that? Let's say you read the patient's blood work and it shows you that the calcium level in the patient's blood is 8.8 milliequivalents per liter. So what it tells you is that patient's blood has 8.8 millimoles of positive charges that are coming from calcium, specifically calcium, in 1 liter. How can you calculate the concentration of calcium using this data? So first, you need to, and the question that asked here is how many moles of calcium are in half liter of the blood. So first of all, we need to find how many milliequivalents are in the half liter. So it's going to be 2 times less than 8.8. It's going to be 4.4. Does that make sense? Mm-hmm. And then, since this is milliequivalents, and to convert it to the moles, we need equivalents without milli, we need to move from milliequivalents to equivalents of calcium. So the conversion factor here would be 1 equivalent per 1,000 milliequivalents. Milliequivalents cancel out. We have 8.8 multiplied by 0.5 divided by 8,000. The answer, intermediate answer, is 0.0044 equivalents of calcium cation in 1.5 liters of the patient's blood. The next question, to get to the very answer. How many moles of calcium the patient has in half a liter? So you know that calcium produces 2 charges, right? It has 2 charges. So 1 mole of calcium will be equivalent, well, sorry for that tautology, but 1 mole of calcium is equivalent to 2 equivalents. Do you understand what I'm saying? 1 mole of calcium gives 2 charges, so 2 equivalents. The conversion factor here will be 1 mole of calcium per 2 equivalents multiplied, that conversion factor, by 0.0044 equivalents of calcium in half a liter. Equivalents cancel out. The final answer is 0.0022.
Can you explain this one more time?
Absolutely. And I'm going to try to do, okay, bear with me for a second. Hold on. I'm trying to insert the empty slide so we can write down something absolutely hypothetical. Okay. So we are, you can't see anything because of the features. Okay. All right. Now, empty page, okay? I'm gonna skip 0.5 liters and, well, okay, let's do this. The average volume of blood of an adult is a little bit more than 5 liters. So let's just presume 5 liters, okay? Just for the ease of calculations. And let's not focus too much on the significant numbers. I just want you to understand the mechanics, okay? So 5 liters of blood. Now, let's say I tell you that for magnesium, you have, I don't know, 4 milliequivalents per liter. You with me? 4 milliequivalents in 1 liter. So my question is, how many moles of magnesium are in the human blood? Warning, disclaimer, numbers are completely off the ceiling, okay? Totally hypothetical. Bearing with me? So, we can start by finding out the total number of milliequivalents of magnesium in the human blood. How would you do that? If there are 4 milliequivalents in 1 liter, how many are in 5? 20. 20 milliequivalents. We're good?
Mm-hmm.
You with me?
Yeah.
Now, then we need to convert milliequivalents into equivalents. So what's the conversion factor?
Can you say that one more time?
We need to convert 20 milliequivalents into just equivalents without milli.
Okay.
So what's the conversion factor?
Just
1
to another.
over 1,000, yes. So that gives us 0.02, I believe. Is that right? Yeah, I think so. Yeah, I think so. Yeah. Does that make sense? Yeah, it's correct. And that the unit will be equivalents. Does that make sense?
Mm-hmm.
The next story, we need to convert it into moles. Now, for magnesium, which has a double charge, what's going to be the conversion factor from equivalents to moles? So 1 mole of magnesium produces how many equivalents? If it has a charge of 2. 2 equivalents. And we multiply 0.02 by this conversion factor, what do we get? 0.01 mole. Does that make sense? We good? Does that explain it? Okay. And finally, if you have 8.8 milliequivalents of calcium, how much chloride you need to balance it out? You need 8.8 milliequivalents per liter of chloride, right? Because it has to be electrically neutral. Does that make sense? Equivalents are often used in analytical chemistry and in medicinal chemistry. I'd be honest, generally speaking, traditional concentrations, they more widespread in classical chemistry. Okay? Any questions so far? So as you can guess, I will ask you to calculate again. I'm not going to ask you anything crazy, but you will have to convert equivalents into moles and vice versa. We're good? Now, solubility. What will happen if you will just keep pouring sodium chloride in the water and will keep mixing it? At some point, will it stop diluting? Yes. Yeah, dissolving, sorry. At some point it will stop. That will happen when sodium chloride will reach its maximum solubility, right? It's like with sugar. You can add more and more and more, but at some point, that is it. Okay? So, every solute has its solubility, which is basically the maximum amount of solute that can be dissolved in a specified volume of a solvent. And it's important to know. Have you heard, you probably have heard about the condition called gout. Okay, yeah, my dad has it. Yeah, so that is a deposition of uric acid in the joints. It may affect hands, mostly affects feet. Okay, it starts usually at the feet, and that happens when the concentration of, uric acid in the plasma reaches levels that are just higher than 7 milligrams per 100 mils. And by the way, uric acid, one of the food products that lead to accumulation of uric acid is alcohol. So it's recommended to avoid alcohol if somebody suffers from gout.
Liver.
Yep. So this is why knowing the solubilities of the chemicals has a pretty good relevance to human physiology. So solubility is expressed in the gram of solute per 100 grams of solvent, usually water. Okay? Now, the solutions in which the amount of solute is lower than the max are called unsaturated. And it's actually, this is incredible, really. So I'm going to talk about unsaturated solutions first. So basically, if you will take, I don't know, a cup of coffee and add a couple of teaspoons of sugar, that will completely dissolve and that's going to be just fine, and you can add more. So that's an example of unsaturated solution of sugar. Does that make sense? Or you can take seawater. You take seawater and, I don't know, you swim in the ocean, you swim in the sea. There's no salt at the bottom because it's unsaturated solution. You can dissolve more. It's fine. Okay. However, there is one, we call it a C, quote-unquote sea, the Dead Sea in Israel, which is essentially a saturated solution of a bunch of different salts, mainly sodium chloride. Okay? If you would look, disclaimer, never been there, have friends who are from Israel, moved here to the States, have been there, went there multiple times. They said, yeah, you walk into the Dead Sea, there's salt at the bottom. Like, the bottom of that lake is made of salt because it constantly precipitates. Okay? It's so saturated. Does that make sense? So, essentially, saturated solutions contain the maximum amount of solute. So if you keep adding, the solute will stay at the bottom. Does that make sense? Now, one concept that I want you to understand in regards to this, when you have two distinct physical states in the same beaker here. Do you see that? You have fluid and you have solid. Correct? So the border between them is called a phase separation border. And you have to understand that the solid salt and the saturated salt solution, they constantly interact. Some ions in the solution form crystals, okay, and precipitate going into the solid. At the same time, other ions dissociate and go back in the solution. You know, it's like you look at a grocery store and you look at the number of people in that grocery store. It's more or less constant, you know, unless there's some massive sale, but it's more or less constant, right? But it's constant because some people walk in, some people walk out. There's always a dynamic. Does that make sense? So same here, there's always a dynamic of some ions going into the solution, some ions going back into the solid state. You clear? Now, something that, not for the exam, but it's pretty cool. You can generate oversaturated solution. Doesn't work always. So basically, you prepare the solution very carefully, basically very slowly adding the solute to the solvent. You can create a solution which contains a little more solute that it's supposed to have. Does that make sense? So say solubility is 10 grams, I don't know, 100 grams per mil per liter, and your solution contains 105 grams per liter. If you prepare that oversaturated solution slow and carefully, what's going to happen? It's going to be all liquid. But when you drop one crystal, one extra crystal, bless you, in that slightly oversaturated solution, it will cause a massive precipitation. It's tremendous to see. Okay? Just one, it's called the center of crystallization. You add one crystal and you immediately have that excess salt to precipitate and form a crystal. That makes sense? This is actually how often crystals are produced. Scientists prepare slightly oversaturated solutions in them, but it has to be slow. That make sense? Another way, by the way, is we will see in this graph, and I'm going to blow it up. You see that graph? So it shows you the dependence of the solubility with the temperature. So you see for the majority of salts, solubility increases with temperature. Does that make sense? Look at glucose. as you will increase the temperature of the solution from, say, 20 to 40, the solubility of glucose will go from 80 to something like 130 grams per 100 grams of water. You see what I'm saying? It will go from here to here. Got it? What you can do to initiate crystallization, you can prepare a solution at 40 degrees Celsius. And then you can start to cool it down very, very slowly. Does that make sense? The solubility will start to go down. And at some point, if you add one tiny little crystal, it will initiate that massive precipitation. That's how crystals can be grown. You can do it at home if you manage to cool it down slowly, which is hard. Okay, but it can be done. Now, for most solids, that is true. I mean, you can see that it's different. The graph's different. For sodium chloride, it almost doesn't change. Okay, it's very frustrating when you try to prepare a really, really concentrated solution and realize, you can heat it up all night long. It's not going to help a lot. But what's important to remember is that for the gas, their solubility decreases with elevated temperature. Does that make sense? It's a law that was discovered by British physicists. Well, they all are physicists, chemists, like all jacks of all trades. Henry. So Henry's law states, and that is true for all gases, it states that solubility of gases decreases as temperature goes up. Does that make sense? So this is actually have this pretty interesting consequences. If you think about a lake, say Lake Erie, in the winter, okay? So say Lake Erie now is fairly warm, all right? Let's give it that, okay? The upper layer is warm. Say it has a temperature, I don't know, 74 Fahrenheit, something like that. 70s, I suppose. And it's getting colder below, but it's not freezing. Maybe it's 60, okay? So upper layer will have less oxygen than the lower layer, because upper layer is warmer. Does that make sense? Imagine it's late fall, the temperature starts to go down, and the upper layer in the lake starts to cool down as well. Does that make sense? As it cools down, it actually starts to accumulate more oxygen. But as it cools down, it becomes heavier. Remember we talked about the changes in the water density? As it cools down, it first accumulates oxygen, becomes heavier, so eventually that oxygen-rich cold water will sink to the bottom, and it will enrich the bottom layer of the lake with oxygen. This is how oxygen is provided to the lower layers of the lakes in the temperate zones. Ohio's in the temperate zone. If you take Florida, there's no winter. It's always warm. So there's no that circulation. Does that make sense? It's actually quite important, Henry's law, for the nature. And I don't want to go into very much details here, but it's also quite important for transport, just a brief sort of description, transport of carbon dioxide. So if you think about human physiology, we get oxygen in the lungs, right? And then that oxygen is transported to the rest of the tissues by the blood. Are you with me? You're bearing with me, okay? So blood on the way back takes carbon dioxide from the tissues to the lungs. You still with me? Good? Now, what is the body temperature? Like there in deep. 95.6, 98.6, you know. Warm. What is the temperature in the lungs? No, it's colder. Because we inhale colder air. Does that make sense? Like air here is what, 75? So lung temperature is much colder than the rest of the body. So carbon dioxide has pretty decent solubility in plasma. Okay? So a chunk of carbon dioxide that is produced in tissues, right? It is transported by the blood from the warm tissues into the cold lungs. Okay? And it can go from the blood into the fluid-covered lungs much more efficiently because fluid in the lungs, and it's normal, it's present there, it's much colder than the blood. So CO2 will go from the warm blood to that cold alveolar fluid very efficiently. Since it's colder and its solubility in that fluid will be higher. Now, another important thing is that if you increase the pressure of the gas over the fluid, its solubility will increase. That's the basis of carbonation. As far as I know, you can now buy a machine that will make a carbonated water, right? Basically the idea, it increases pressure of CO2 over the fluid. When you have a closed can of soda, the pressure of carbon dioxide above cola is the same as in cola. Does that make sense? You open the can, what happens to that CO2 above cola? It goes out. It does pss, right? And what's going to happen to that cola? Eventually, it's going to lose all the carbonation, right? It's going to become kind of stale, right? So that's your physical basis, how it happens. Now, despite the fact that we constantly talk about salts being strong electrolytes, not all the salts are soluble in water, as you now know, okay? And here are some rules to remember. Lithium, sodium, potassium. All salts are soluble. I would add all common salts are soluble. Okay? Ammonia, soluble. Nitrates and acetates, soluble. For chloride, bromide, and iodide, all are soluble except for silver, lead, and mercury 1. The formula of that particular ion is like this. So this ion is formed by 2 atoms of mercury. For sulfate, there is like a whole bunch of stuff, okay? Calcium, strontium, barium, lead, they're insoluble. In fact, there is one cation for which there's only one soluble salt. It's sodium silicate. So sodium silicate is soluble in water. But if you make it a little bit more concentrated, it will start to make really weird looking structures. If it will start precipitate, it is sometimes referred as a liquid glass, because silicate is the basis of the glass. And water solution of sodium silicate is sometimes referred to as liquid glass. If you cool it down, it will, or evaporate it a little bit, it will start to form interesting shapes. Silicates are incredibly insoluble. Does that make sense? So knowing these solubility rules, you can quickly determine, for instance, that potassium sulfide is soluble, okay, contains potassium. Calcium nitrate is soluble, since it contains nitrate. Lead 2 chloride is insoluble because it's, well, lead. Sodium hydroxide, sodium, everything sodium is soluble. And aluminum phosphate, insoluble, because aluminum, not everything soluble, and phosphates, not everything soluble. That makes sense? But I'd be honest with you. My personal opinion, if you're not working in analytical chemistry, in qualitative analysis every day of your life, knowing solubility, basically if you know that lithium, potassium, sodium soluble, nitrate and acetate soluble, that's more than enough. Does that make sense? For everything else, we used to have a solubility table in the classroom on the wall. Now you've got Google. So you look up solubility. And it's perfectly fine with me. Because that's the type of information that you don't need. If you don't need it every day, you don't need to waste your time and effort to memorize it for some obscure reason. And if you need it every day, you're going to learn it in 2 days. Does that make sense? Now we're going to chat a little bit about the concentration, the calculations. And I want to say to you that give you sort of a little, not a rant, but sort of a pep talk. I tell you every time that chemistry is the very visual science. Concentration is the very visual concept. It has nothing to do with math. It's basically the number of something, the amount of something in something else. So when we say a concentration, we talk, say, 5 milligrams in 1 liter. It means that there is 5 milligrams of something in 1 liter of solvent. Does that make sense? We can say that the density is another example of concentration. It's the amount, it's the mass in a certain volume. Does that make sense? You understand what I'm saying? So you always have to think about concentration as physical particles in the restricted volume or restricted mass or something else. You understand? So, for instance, here is an example of a preparation of the solution of potassium iodide in water. Okay? So, you can use all the math you want, but in my opinion, it's like really important to understand this. Look at the conditions. You have 5 grams of salt. And these 5 grams of salt are diluted in the water sufficient to make 250 mL of the solution. So what's the concentration? It's 5 grams into 50 milliliters. I mean, it's not conventional units. Conventional units, bless you, will be, say, a liter. Does that make sense? So, how many milliliters are in 1 liter? Milliliters. 1,000. Yeah. Nothing hard. Nothing hard. 1,000 mils. So, if you have 5 grams into 50 mils, how many grams are you going to have in 1,000? Math quizzes. Huh? Say again?
40.
No, not 40. So 250. It's the fraction of 1,000, right? What is the fraction? Like 1/4. 1/4. Okay. So if you have 5 grams in a quarter of a liter, right? How many grams are you going to have in the whole liter? 20. 4 times more. Does that make sense? If you have 5 grams in a quarter of a liter, you're going to have 4 times more in the entire liter. You understand what I'm trying to say? And I told you before, we used an example of like apples in a bag. That's the same idea. If you have 5 apples in 1 pound, how many apples are you going to have in 4 pounds? 20. When it comes to groceries, it's not an issue. That's the same groceries, we just changed the units. We clear? Any questions? We're going to wrap it up. I will see you in a bit in the lab.